So the first main topic for the second half here is to look at our fractions in a bit more detail. We mentioned that fractions are those two parts, the count and the name. So when we have 3/4, this is saying we have 3 of something. Just like 3 cows, 3 inches, 3 pounds, or whatever. Here we have 3/4. So our first step is to define what it means to be a fourth. Well, not to go too far back, but the easiest way to illustrate that is to use the old elementary school illustration of a pizza or a pie or however you want to put it. Fourths means we take that pizza and we cut it into 4 equal pieces. Pretend those are equal. Or so it takes one object is cut into 4 equal pieces, or you can think of it as being it takes 4 pieces to make one object. And since this is 3/4, that means we have 3 of those 4 pieces. No comments on my coloring skills, please. The first big thing we're going to need to do, we saw with 1/3 and 2/5, we couldn't combine those because of their names. But if we change their names, we can combine them. So the first skill we need to do with fractions is learn how to rename them or change their names. From this illustration, the simplest way to show that would be to do this. If I can draw a little bit. I'm going to cut each slice into 3 equal pieces. Again, pretend these are equal. Now, how many total slices does it take to make a whole pizza? Careful. 12 of them, right? We had 4 and we cut each of them into 3 equal pieces, so 4 times 3 is 12. You're looking at 2? Yeah. Okay, so now how many slices do we have in yellow there? 9. We had 3. Each of them got cut into 3. So 3 times 3 is 9. Do we have any more or less than we did before? No, it just looks different. So 9/12 has exactly the same value as 3/4. And that was because we multiplied by 3/3. Which, of course, that's saying it takes 3 pieces to make a whole object. We have 3 of them, so we have 1 whole object. So we multiplied by 1. And whenever we multiply by 1, it doesn't change the value. It can change the appearance like we saw here, but it doesn't change the value. The tricky part with fractions is figuring out what we're going to use to change it. Here we just randomly picked 3. But often we'll end up with a situation like this, where we might have 2/3 and we need to change it into 15ths. So we have to decide, what are we going to multiply 3 by to turn it into a 15? 5. Perfect. So you multiply 2 by 5 to make 10. So 10/15 equals 2/3. If we need to go the other direction, we can reverse that. We multiplied by 5 on top and bottom to get to 10/15. To go backwards, if we divide by 5 on both the top and the bottom, both the numerator and denominator, 10 divided by 5 is 2. 15 divided by 5 is 3. We get back to the 2/3. We've already established that those are equal. So again, here, we saw that it was multiplied by 5, so we need to divide by 5. The tough part can be looking at the fraction, figuring out what we can divide both numbers by, or what we should divide both numbers by. We might have 48/60. Now, a lot of us were taught that when you go to reduce a fraction, you have to find something called the greatest common factor. That's the largest number that will divide into both the numerator and denominator. Which, it's easier if you find that, but you don't have to. Like, I look at these, and the first thing I see is that both of them are even, which means I can divide them by 2. So if I go ahead and divide by 2, I have 24 and 30. Now, obviously, I'm not done reducing it, but at this point, there's smaller numbers, and it's easier for me to see what I can divide them both by. They're still both even, so I'm going to divide by 2 again. 24 divided by 2 is 12. 30 divided by 2 is 15. Well, the 2's aren't going to work anymore, but now that they're smaller, I can see that both of them can be divided by what? 3. 12 divided by 3 is 4. 15 divided by 3 is 5. I can run into things like this. This is what we call an improper fraction. Now, improper implies there's something wrong with it, and there isn't. There are actually times we prefer to have them set up like this. They're called improper just because the numerator is bigger than the denominator, which means we have enough pieces to make at least one whole object. In fact, here we can make several whole objects. One of the things that students always say is, well, we just divide it. Well, there's some truth to that. But here's a place where you have to be careful. If you were to just punch this in your calculator, 44 divided by 7, it's going to spit out something like 6.28571429 approximately. Well, that doesn't help us. Well, it does a little bit, actually. It does tell us that we can get 6 whole objects out of there. But it doesn't tell us how many pieces are left over. The fact there's a decimal says there are pieces left over. So this works better if we just do it as a long division with a remainder. 44 divided by 7. 7 does go into 44 6 times. What's 6 times 7? 42. So there is 2 left over. So 2 sevens. So that's 6 and 2 sevens. Going the other direction, this, of course, is what we call a mixed number, because it mixes whole numbers and fractions, whole objects with pieces. If we go the other direction where we have a mixed number like that, like 3 and 4/5, and we want to turn it back into an improper fraction, what we have to do is take these whole objects and break them into pieces. Where do we find how many pieces each of them becomes? The denominator of our fraction tells us how many pieces are in a whole object. So that 3 whole objects, we break it up into 5 pieces each. So in other words, we take 3 times 5, which is how much? 15. So that makes 15 pieces. We already had 4 pieces here. So we're going to add that 15 to our 4, get 19 fifths. I'll do one more example of that. If we have 7 and 1/3. Just do the whole number times the denominator. 7 times 3 is 21. And we add that back to our numerator. 1 plus 21 is 22 thirds. The nice thing about math is pretty much everything, well, everything is reversible. So if you weren't sure, go ahead and divide that back out. 22 thirds, is that going to give me back 7 and 1/3 when I change it back? Isn't it better? Okay, so on to our operations. I know I went through that kind of fast, but just kind of a little review. Hopefully you already know how to do the conversions. If you don't, let me know and I can give you some material to help you out with that. So we had seen something like 1/3 plus 2/5. They don't have the same name. When I do my addition, I like to do addition and subtraction vertically because I'm used to lining stuff up. So I'm going to set this up vertically. Our first step is to figure out what that same name or common denominator is going to be. There are several strategies for it. One is you can just multiply them. 3 times 5 is 15. That'll give you a common denominator. And we were always told you had to use the least common or the smallest common denominator. That's not necessarily true either. Any common denominator will work. It's a little more work if you have a bigger one. Here, 3 times 5 would be the smallest one. Another method, you can just make lists. So you put each denominator down and you count up. So this is 3, so we're going to count up by 3s. 3, 6, 9, 12, 15, 18, and so on. This denominator was 5, so we count up by 5s. 5, 10, 15, and there we have our match. It's 15. There are other more complicated methods using factoring and stuff like that we won't get into here. If you're interested in it, let me know and I can post some videos and stuff on Blackboard for you. So what we've come up with is that our common denominator has to be 15. What's going to have to go up here? 5. Good. 3 times 5 to make 15. 1 times 5 makes 5. What'll go here? 6. Good. It was 5 times 3 to make 15. 2 times 3 makes 6. 5 plus 6 is 11. We combine our counts. We keep the same name, 15. I'm not going to spend any more time with simple fraction addition. I'm going to jump up to mixed numbers. So let's say I have 8 1/3 plus 5 3/8. My first step is to find a common denominator. For 3 and 8, what's that common denominator going to be? 24. Now, a lot of textbooks don't rewrite the whole number when they find the common denominator. I do, because I found if I put this new fraction with the common denominator over here, I a lot of times forget about the whole numbers, so I always bring them over with me just so I don't lose them. But you don't have to. If you were taught not to and then you're like that, you don't have to worry about that. What's going to go up here? 8, right? 3 times 8 makes 24, so 1 times 8 is 8. What goes here? 9. Good. 8 times 3 to make 24. 3 times 3 makes 9. And now we're going to add. Notice the fractions at the end of the number lined up almost just like it's the last digit of the number. And actually, that's all it is it's the last digit of our number. So we're going to add just like we would whole numbers, starting at the end of the number on the right and working our way back to the left. So we combine this last digit first, the fractions in this case. Combining the counts, 8 and 9 is 17. Keeping the same name, 24. We move over. 8 plus 5 is 13, so 3, carry the 1. And there it is. If it can be reduced, reduce it, yeah. And we run into stuff like this, like 7 5/6 plus 5 3/4. Common denominator is going to be well, 6 times 4 is 24, but there's a smaller one that'll work. 12, good. 6 times 2, so 5 times 2 is 10. 4 times 3, so 3 times 3 is 9. So now I'm starting on the right and working my way back to the left here to add this. 10 twelfths and 9 twelfths. 10 and 9 is 19 twelfths. Now we see the problem there. That's an improper fraction. I can take one whole object out of there. I can take 12 out of 19 once. And how much is left over? 7. So 7 twelfths. So we keep the 7 twelfths and we carry the 1. 1 and 7 is 8, plus 5 is 13. So 13 and 7 twelfths. Any questions so far? Subtraction's a bit more difficult. We're going to start right in with mixed numbers. Eight and 7/8 minus 2 and 2/5. What's my common denominator for 8 and 5? 40. Okay. What's going to go here? 35. Good. 8 times 5 to make 40. 7 times 5 makes 35. What'll go here? 16. Perfect. 5 times 8, so 2 times 8. Now we subtract, just like with our addition. We treat that fraction as it's the last digit of our number. We'll start at the end or at the right and work our way back to the left. 35 minus 16 is 19. And we keep the same name, a 40th. 8 minus 2 is 6. It can get a little worse than that. Here, 9 and 1/4 minus 2 and 5/6. We need a common denominator, which is going to be what? 12. Good. So what's going to go here? 3 on top. Good. Yeah. 4 times 3, so 1 times 3. And here you said 10. Yes. 6 times 2, so 5 times 2. We go to subtract. Working right to left again. 3 minus 10 gives us a problem. So what do we have to do? Just like any other subtraction, we're going to borrow. That 9 becomes an 8. But unlike our other subtractions, I can't just put a 1 in front of something here. What I borrowed was one whole object. And where do we find out how many pieces are in that object? Our denominator. There's 12 pieces in the one object that we borrowed. So we have to add 12 to the 3 to get 15 12s. Oops, come on. I may have just lost word here for a second. Yep. Give me just a second, I'll restart Word. I'll pause the recording so those of you that are looking at the recording don't have. What was the problem again? Minus 2 and 5 6. Thank you. And we had common denominator, so this was 3 twelfths and 10 twelfths. And we were in the process of borrowing. We borrowed from the 9. That's an 8. And we said the denominator told us we had to add 12 to the 3. So that's 15 twelfths. So now when we go to subtract, it's 15 twelfths minus 10 twelfths. So 15 minus 10 is 5 twelfths. 8 minus 2 is 6. We'll do one more example of that borrowing tends to trip people up. So let's say that we have 7 1/3 minus 5 4/5. What's our common denominator? 15. This will be 5 and this will be 12. So again, we go to subtract. 5/15 minus 12/15 is an issue. Borrow from the 7 to make it a 6. What do we do to our fraction? We have to add 15 there. So 5 plus 15 is, yes, 20 over 15. Now we can subtract 20 minus 12. 8 15ths. And 6 minus 5 is 1. Any questions? Okay. Time to move on to multiplication. If I have something like 3/4 times 2/5, when we multiplied, we said earlier, we combine counts and we also combine the names. And we even did an example where you could see in fractions, that just meant you multiply straight across. 3 times 2 is 6. 4 times 5 is 20. Now with what we saw earlier, we know that we can reduce that. Both 6 and 20 can be divided by 2. 6 divided by 2 is 3. 20 divided by 2 is 10. So we get a reduced answer of 3/10. Now some of you might be looking at that thinking, why didn't you cross cancel or cross multiply, it's sometimes called. Others right now might be wondering, what's cross canceling? Well, what it is since we know we're going to combine the 3 and 2, you get 3 times 2 on top, and combine the 4 and 5 to get 4 times 5 on bottom. Rather than multiplying them out and reducing like we did here, we can reduce before we multiply. We can see that 4 and 2 can both be divided by 2, and do that before we do the multiplication. We can cross cancel 4 and 2 dividing by 2 to give me 2 and 1, like that. Now when we multiply, 3 times 1 is 3, 2 times 5 is 10. We get our reduced answer without having to reduce later. We reduced before we multiplied, basically. Now, in a problem like this one, it's about the same effort to do it either way. But we can run into problems like this. (24 25ths) times 35 36. Here, we could go ahead and multiply this out and reduce it, but 24 35ths ends up being 840, or 24 times 35 ends up being 840. 25 times 36 ends up being 900, and then we'd have to reduce that, 840 over 900. which we could reduce, but it would take some time. But if we look at this, we can see, hey, 25 and 35 can both divide by 5. 25 divided by 5 is 5. 35 divided by 5 is 7. 24 and 36 can both be divided by... There's a lot of possibilities there, isn't there? 6 would work. 24 divided by 6 is 4. 36 divided by 6 is 6. We see that they can both still be divided by 2. 4 divided by 2 is 2. 6 divided by 2 is 3. You can see, just like with reducing the fractions, we can keep reducing in our cross-canceling. So now it's 2 times 7 is 14. 5 times 3 is 15. You get 14/15. That is what this would reduce to if you wanted to do it. Okay, again, we're not going to keep going with the simple fractions. We're going to jump up to the mixed numbers. So let's do something like 7 1/3 times 5 1/4. Multiplying mixed numbers is actually an extremely difficult concept. In fact, I bet if you walked to any four-year university and found 10 math majors and asked them how to multiply mixed numbers, I would be shocked if any of them could show you how to do it correctly. So how are we going to do it? Well, when we multiply mixed numbers, we cheat and we convert them usually into improper fractions. Good. What does 7 1/3 become? 22/3, yes. 7 times 3 is 21, plus 1 is 22. 5 1/4 becomes? Perfect, 21. 5 times 4 is 20, plus 1 is 21/4. Notice the denominators never change. Now, just like any other multiplication, we can cross-cancel here. 4 and 21, or 3 and 21 can both be divided by 3 to give me 1 and 7. 4 and 22 can be divided by 2 to give me 11 and 2. So now, 11 times 7 is 77. 1 times 2 is 2. The difficulty here is we have to reduce it back down into a mixed number. So we do our division. 2 goes into 7, that's 3 times, 6. 1 left over. Bring down the 7. 2 goes into 17, 8. 2 times 8 times 2 is 16, so there's still 1 left over. So there's 38 1/2. Anybody want to see how to multiply the mixed numbers just for fun? No? Okay. No sadists in here? No. You know, it used to be every year somebody would ask. Now, the last like 2 or 3 years, nobody wants to see that anymore. Oh, well. It's a lot of steps. It is. But, you know, you have kids someday and you want to punish them. No? I always thought they should let me go teach math in the prison system. There would be a lot less repeat offenders. So anyway, sorry. Let's do one more example of multiplying the mixed numbers. Let's say we have 4 3/8 times 2 4/5. I'm going to give you guys a minute to try that in your notes, and then we'll go over it in about 1 minute. Okay, so our first step is to make it into an improper fraction. 4 3/8 becomes 35/8. There we go. Be brave. 2 4/5 is 14/5. Perfect. Now we can reduce it. We can cross cancel. 35 and 5 will give me 1 and 7. 8 and 14 will give me 4 and 7. So we have 7 times 4 is 40, or 7 times 7 is 49. 4 times 1 is 4. We'll divide that out, I get 12 1/4. How many of you had 12 1/4? Okay. Now for those of you with like a TI-30 or a Casio FX fraction calculator, you may know how to enter that in the calculator and get that answer, which is wonderful, but I will warn you on our first test, It's 4 pages, and the first 2 pages you're not allowed to use a calculator on, just so you know. And that'll be operations with fractions, decimals, and whole numbers. Yeah, I know. It's not as scary as it sounds. I try to be nice. But just making sure you can do them by hand. I don't mind if you go back after you've done them and punch into your calculator to check to see if it's right. But I do require you to show your work on those. See, that's the only time I will ever mark you wrong for not showing your work. But for those, you got to show your work or you won't get credit for them. Otherwise, showing your work on your tests is just how you get partial credit. If you've got the wrong answer, I'll look at your work and see if you've done anything that'll get you part of the points. So just my little warning, make sure you can do some of these by hand. Okay, so that's multiplication. Let's take a look at division. Now, we've said before that multiplication and division are the same operation, just one's going forward and the other's the reverse. So let's say I have 2/5 times, what do I do? Let's go times 3/5. We just multiply straight across, right? 2 times 3 is 6. 5 times 5 is 25. Does that mean I could do 6/25 divided by 3/5? And I could just divide straight across? Can I do 6 divided by 3 is 2. 25 divided by 5 is 5. Gave me the right answer, right? Actually, that is the right answer. Does that work every time? Actually, it can. It does kind of depend on the problem. We have to force it sometimes. How are we taught to divide? Well, the reason why we don't do it that way all the time, by the way, is because we do run into problems like this. 3/4 divided by 2/3. Where, hey, 3 does not divide by 2 evenly. 4 does not divide by 3 evenly. How are we taught to do a problem like this? Okay. Yeah, the first fraction, the 3/4, doesn't change. We flip the second one. It's called the reciprocal. So 2/3, we flip it over to be 3/2, and then we multiply. Some of you may have been taught something called the zigzag method or something like that. It looks like that. That's a gimmick that one of the things I kind of dislike. But if that works for you, great. As long as it works for you. But anyway, so we found this reciprocal. Now we're going to multiply. 3 times 3 is 9. 4 times 2 is 8. 9/8, or reduce that to 1 1/8. Believe it or not, what we just did there, multiplying by reciprocal, came from this process right here, just dividing straight across. Let me show you how. Once upon a time, when we divided, it's kind of like I showed you with the addition, how you, instead of carrying, we could add from the left to right and then drop the numbers and re-add them later. Processes have evolved over time. We didn't always multiply by reciprocal to divide. Well, in my lifetime, it's been a few hundred years that we've been doing that, so I don't remember when we didn't. But before we used the multiplying by reciprocal, what they would do is this. They would look at this second fraction, 2/3. What is 2 times 3? 6. They would use that 6 to rename the first fraction. They would multiply by 6 on top and bottom. What's 3 times 6? 18. What's 4 times 6? 24. Notice 18 24ths and 3/4 are the same number, just they look different. Now we can divide by 2/3. What's 18 divided by 2? 9. And 24 divided by 3? 8. So it's 1 1/8. So how on earth did we get from this to multiplying by reciprocal? Well, at some point, somebody looked at this here, and they realized, hey, if I violate my order of operations just a little bit, and I do this division first, 6 divided by 2 is 3, 6 divided by 3 is 2. What I always get here is just this fraction flipped over. And so they named that reciprocal, and then said, okay, now we just have to multiply that by our first fraction. So that whole idea of multiplying by reciprocal is a shortcut that comes from this much longer process. it's not going to change the way we divide fractions. It's just a little bit of math history so you can see where it came from. Let's take a look at some mixed numbers here. 7 1/4 divided by 2 2/3. Now, since we're going to turn it into multiplication, it makes sense that we start out the same place we did with multiplication, which is turning these into improper fractions. 7 1/4 becomes 29/4. 2 2/3, 8/3, right? Can I cross cancel the 4 and the 8? No, because right now this is still division. Okay. The next step, we're going to, the 29/4 doesn't change. The 8/3, we're going to make it a reciprocal of 3/8. Now this is multiplied. Here we could cross cancel, but there's nothing to cross cancel in this case. So 29 times 3 is 87. 4 times 8 is 32. 87 divided by 32. 32 goes in there twice, which would be 64, with 23 left over. So that's 2 and 23 32nds. Look familiar? Okay. Again, like I said, I'm not going to do a lot of examples because it's kind of review at this point. But with my fractions, there is something I want to point out. You know, when we did like 2/9 times 3/4, we were able to cross cancel the 2 and the 4. Basically what we were doing was this. We're leaving that as a 2, and we're factoring that 4 into 2 times 2, and that 9 into 3 times 3. And we could cross cancel. We could cancel out a 2 there, so that's 1 and 2. Cancel out a 3, so this is 1 and 3. Well, this is a very powerful tool, that cross-canceling within our fractions, when we do start to include other names, other labels within it. For example, we might have 3 feet over 1 as a fraction. And when we go to convert measurements, we use unity fractions or conversion factors. If I put 1 foot on bottom and 12 inches on top, I'm going to stop for a second. What does that equal? 12 inches over 1 foot. That's the same thing. So it still equals 1. It doesn't look like it, but it's the same value in the numerator as in the denominator. So that's still a fraction that's equal to 1. When we multiply by 1, it does not change the value. It just changes the appearance. So what's happening here, we can cross-cancel not just numbers, but units. We can cross-cancel the feet. So it's 3 times 12 inches is 36 inches. 1 times 1 is 1. So 3 feet becomes 36 inches. That's one of our methods, the one that we're going to use the most for converting measurements. Also, let's say that you have an IV that is set to run at, I don't know, 3 milliliters per minute. And you have a drop factor of 12 drops. GTT is the abbreviation for drops per milliliter. What this here, 12 drops per milliliter, what that means is 1 milliliter equals 12 drops, or contains 12 drops. So if we want to convert our flow rate from milliliters per minute to drops per minute, we can use this idea of fractions. So this is 3 milliliters. 3 milliliters per minute is really 3 milliliters over 1 minute. When we talk about ratios, we'll talk about that a little bit more. And we can multiply that fraction by, now if we're trying to, we want to leave the minutes, we want to change the milliliters into drops. So to get rid of milliliters, I'm going to put them on bottom so that they cancel out. 1 milliliter equals 12 drops. So again, this is a unity fraction because 12 drops and 1 milliliter are the same amount. Yeah, so we can cancel out the milliliters. It's not 12 drops though, it's 3 times 12 is 36 drops over 1 minute. So 36 drops per minute. This tool, which is just cross-canceling with the labels rather than just the numbers, is called dimensional analysis. It is a tool. We'll revisit it again in the next unit with our measurement conversions. And then when we do our dosage calculations in Unit 3, it is one of the methods we will use to do our dosage calculations. We have dosage calculation formulas, but there are different formulas for different types of problems. Dimensional analysis can be used to solve any problem. And that's why I like it. I mean, that's the main method I use. And I'll show you guys all three methods that there are to do our dosage calculations and let you guys choose which one you like. But the dimensional analysis is really kind of nice because you really don't have to remember anything. You just have to match up the units. And the units tell you what you have to do with the numbers. Like here, I didn't have to know that I had to have the 12 drops on top and the milliliters on bottom. The fact that there was milliliters here and I was getting rid of milliliters told me I had to put milliliters on bottom, so they canceled out. Okay. Well, one of the other things that we're going to touch on is what if we have a problem that looks like this? 18 minus 2 times 5 plus 3. Well, doing a problem like that, some of us might look at that and say, hey, let's just go left to right. That's how we read, right? You start in and say, well, 18 minus 2 is 16, then times 5 is 80, plus 3 is 83. Notice I didn't write that down because that would not be the correct answer. There's a lot of different ways you could look at this and interpret it. And now I've said that there are different ways to get to the correct answer, but we still have to, there is still only one correct answer. So we have to get to the same correct answer in the end. In order to make sure that we look at a problem like this and everybody gets the same answer, we've defined something called the order of operations. Ah, good question. That is 2 times 5. That's the same as the x. We just use the dot for multiplication, just so when you put in x's for variables, it doesn't confuse you more. Order of operations, you guys have probably already seen, like the PEMDAS, parentheses, whatever. I'm going to put in enclosing symbols for the top one instead of parentheses. I know that screws up your mnemonic, but enclosing symbols include parentheses, but there's also fraction bars, root symbols. There are other enclosing symbols. Second is our exponents. We haven't really talked about them yet, but exponents include powers and roots. Third, multiplication and division. And fourth and finally, addition and subtraction. Now, most people view these as a set of steps, and that's not really what they are. What they really are is levels of priority. The things at the top of the list have priority at the things at the bottom, so they have to happen first. So looking at our problem here, the highest level of priority is the multiplication, 2 times 5. That's 10. So I take out the 2 times 5 and I replace it with 10. I also get the question all the time, well, is that 2 times 5 or is that negative 2 times 5? The answer to that question is yes. What do I mean by that? Well, I'll show you. I can do that as 18, and I can treat it as a negative 2 times 5. But if I do that, what I have to do is I have to change this to plus a negative 2. 18 minus 2 can be thought of as 18 plus a negative 2. So then when I do that, negative 2 times 5 is a negative 10. This is 18 plus a negative 10 plus 3. Or here you can see I just chose to do it as 2 times 5, so it's 10. It's 18 minus 10 plus 3. 18 plus a negative 10 and 18 minus 10 give you the same result. It's just simpler for me to think of it as subtracting a positive than it is subtracting or adding a negative. Now, all that's left is subtraction and addition. Those are on the lowest level of priority. If there's more than one operation on the same level of priority, we go left to right, just like reading a book. So we do the 18 minus 10 first is 8. plus 3 is 11. So if we look at a little bit more complex problem like this, but still relatively simple, here we have the enclosing symbols. So we have to look inside the parentheses first. Inside there, order of operations do still apply. We have to make sure there's no other enclosing symbols, no exponents, but we do have multiplication. So 6 times 3 is 18. So I replace the 6 times 3 with 18. We're still inside the parentheses. 8 plus 20, or 8 plus 18 is 26. Whenever we've reduced what's inside an enclosing symbol to a single number, I can get rid of that enclosing symbol. So I can take away the parentheses. I do have to be careful here. What do I have to make sure I do? The 2 was in front of the parentheses with no operation. That's implied to be multiplication. So when I take out the parentheses, I do have to put multiply in there. So now we have 2 times 26 is 52. It's just 7 plus 52 is 59. Any questions on that one? Okay. We might have, oh boy. Something like this. I'll be careful here. We'll do that. On a problem like this, we need to define what that line across there means. What does it mean? Okay, it means divide. Most people say divide, and it does mean divide. It's called a fraction bar. It is telling us that we're going to have to divide something. It's also an enclosing symbol. It separates the top of the problem from the bottom. So it's telling us that we have to do everything on top first, then do everything on bottom, and then divide. So on top, what would we have to do first? I'm going to move it over here. What would come first there? Multiplying, right? 3 times 5 is 15. Moving left to right, then we would have to do the 7 times 3, right? A lot of people ask me, well, can't I just multiply both of those in the same step? In this case, you could get away with it, but there are some cases where you can't. So it's always safest just to do one at a time, and each step do the next piece. So then we have 15 plus 21 does make 36. That's our total on top. What do we do first on bottom down here? Parentheses, 9 minus 7 is 2. Now I'm going to take out the parentheses because I'm down to a single number. So all that's left is 3 times 2, which is 6. 36 divided by 6 is 6. So that's it. Any questions? Okay, I'm not going to go over every type of possible order of operations because hopefully you guys have seen it before. And if you haven't, that's where we'll start out next week, is answering questions on that. So I don't have the website up, but homework that goes along with this stuff. If you look at the homework sheet, I'm just going to list the pages. You guys can look up on that assignment sheet in Blackboard. Pages 7 through 8, pages 18 through 21, page 23, and page 29 through 32 go over the material that we covered today, and a little bit that we didn't cover is kind of review material. If you have any questions on that, like I said, we'll go over that to start off the class next week. As you're doing the homework, you'll notice, remember on Blackboard, the solutions to all the homework questions are there. As you're doing the homework, usually I say just do the odd numbered problems. It cuts it down a little bit. I'm not about making you go home and do like 80 problems over the week. But Also, if you do the first couple and they seem really easy, and at the beginning of the semester here, for a lot of you, they might. Feel free to do the first couple and then just skip ahead 4 or 5 problems and do some of the more difficult ones. I'm not grading the homework. I don't want you to go home and do busy work on stuff you already know how to do. So make sure you do enough that you're ready to take a test on it. But if it's really easy and you know it, skip ahead a few problems. That won't offend me, I promise. Okay, so that is about our time. Anybody has any questions? We got a few minutes left. Otherwise, have a great week.